Thank you. Good afternoon today. So I would like to present my work named the Edge-Level Graph Neural Network Architectures for Network Intrusion Detection and Advancing Beyond Standard Edge-Level Classification. So I was supported from my company. Currently, I am working at Siemens, located in Istanbul, Turkey. Basically, they were so they actually supported my article. So let me explain it a little bit. So currently you see a picture in which SCT is connected on IoT, let's say. So in every building, as you see, there are basically a lot of devices that are connected to the cloud, as you see, all of them, like the clouds, are located in different parts, as well as they are actually a lot of kinds of clouds, as you see, like healthcare, like the automobiles, the mobile things, and so on, actually. Also, I can mention that if we take a closer look on the picture, we see that it has a wide scale, actually. And also we can say since we have lots of kinds of clouds, as you see, the communication between these devices can be heterogeneous as well. And also, as we also mentioned, like the people use these devices, so which will create a dynamic device integration, as well as the huge amount of data, which will basically cause some security issues, actually. So because since the data is huge, the devices are dynamic, the communication always fits, and we might have a security challenge, actually. And here comes our research problem, actually. We want to find some intrusions on big IoT data. And if we have a big IoT data, how can we find it, actually? So that is to say, and we in my research, I mainly focused on the RAV packets sent between the IP addresses of some devices, actually. And if we do a little bit regarding literature review, since our main focus is finding network intrusions between the entries, in which basically shows route packages between IP addresses. The first approach that came to our mind is actually a lot of companies are doing that. They are mostly using traditional network intrusion detection systems, actually. Here, in general, the network-based intrusion detection systems, a lot of companies are doing that. They are actually putting the system which is connected to the firewall, as you see, and some network switches around. This is kind of a main architecture, so to say. Small changes between, but still we actually place firewall and network-based intrusion detection system to connected to each other, and basically the attackers are knowing that. And always we have the same main architecture, same configuration of these devices, which will basically fails to detect zero-day attacks. That's because since these attacks are do not exist in the literature before, we need to find some meaningful situations between these IP ROC packages, actually, and which will basically yield us to detect some zero-day attacks, actually. And the second part of this literature review is the machine learning, in which we actually saw that with the IoT data, we saw some algorithms like random forest, which will basically use the decision tree mostly, support vector machines, which will basically use margins of the data and then try to fit the prediction. And then also we also see some examples of the k-nearest neighbor algorithm, which will basically the nodes are aggregated with respect to their neighbors. They actually have high accuracy, And we also saw in the latest times, like let's say more than 2022, there were some algorithms emerged like CatBoost and XGBoost. They also have more accuracy as well, like more than the random forest, support vector machines, and k-nearest neighbor. But they actually have some logic in which they generally treat the connections independently. So they treat the IP addresses which are sending raw packages. They treat these connections independently. They don't basically take care of the relations between them. But we also know that these relations can be rich with respect to the IoT architecture. So here in this step, some deep learning algorithm comes in the literature as well. Mostly in the deep learning, the convolutional neural networks are used, which basically has the architecture of the images. But there were some articles as well which are using this convolutional CNN with the time series. And also we saw some examples of the RNN which will basically take yield of the sequential dependency of this of the connections actually. And then we also saw some examples of the LSTM, which will basically take care of the temporal dependency, always remembers the output of like previous outputs, let's say, and create a meaningful prediction based on this. And we actually see that in the IoT data, if the data is huge, we need to handle this data with dependent and independent dependencies and connections, let's say. So it's a little bit complex than that. And sometimes it might be a good idea to use some of these deep learning algorithms and combine them. So this, which will basically give us the idea of our work. I will explain that. And we also saw some examples of the graph neural networks. So the graph neural networks has the core idea of message passing, which will basically aggregate the information with respect to neighbors of these connections, which will basically give us the idea we can make a meaningful prediction based on the dependencies of the connections, actually. So that's the core idea of the graph neural network, and we thought that it's a good idea to use it. And here, actually, we also saw that the graph neural networks examples, we see three kinds of it: the node level, edge level, and graph level. So in node level, actually, if we have a graph like this, where we see the alphabets like A, B, C, E, and they are actually they can show the IP addresses, and the connections between them are the packages sent between them. So if we can say the connections are the raw packages sent between these IP addresses. And if we take a closer look on one node, let's say one IP address, if that shows attack pattern or not, that means we have a node level graph neural network. But if we want to take a closer look of the connection, the raw package, instead of a node, then we are actually investigating the connection between these IP addresses, which will like show us the attack pattern or not. So and the graph level is since the graphs can be huge with respect to the amount of the IoT data, we can say this: if the small part of this neural network if the small part of the graph does it show like attack pattern or not, if we are investigating this an amount of graph, let's say a part of the graph, then we are investigating graph level neural networks, actually. So that's the distinction between them. And our methodology is basically based upon this edge level GNNs, and we investigated three of the graph neural network algorithms, we have actually created them, and we actually create one another, which is the edge-level graph convolutional neural network, that in which we see some examples on the literature, and we thought that actually it's a nice idea to compare our three methodologic algorithms with this baseline, actually edge-level graph convolutional neural network. And I can explain one by one right now. So it's the edge-level graph convolutional neural network is what it does is it has it basically used three-layer neural network with the ReLU function and then the batch normalization. With this three-layer, they actually do node encoding, and they are also using one layer which has kind of the same structure, like using ReLU function and also the batch normalization. With this one layer, the EdgeLevelGCN does the edge encoding, and basically, and then after the encoding is done, we are concatenating them, basically creating a one big array that puts basically the encodings, all of the encodings actually, and then we apply three-layer classifier again to diminish the dimension as 2, and then start predicting it. So this makes it baseline actually, because we actually thought that we are using some components that mostly used in the literature and which doesn't show the novelty actually. So that's our baseline to compare our new algorithms. Let me investigate them one by one as well, the new ones. So the prototype graph neural network, it really resembles the EdgeLevelGCN, but except it basically applies the prototype projection. What it means is it will, after the encoding step, it will create 16-dimensional prototype, which basically we apply some neural network, and then after the encoding step and the concatenation, we apply neural networks to reduce the dimension as 16. That's the parameter that we are using actually. So this is the 16 is interchangeable, and you can easily change it. That's the core logic of the Prototype-GNN actually. And as soon as we have actually created this prototypes, with the new data we start investigating the distance with the prototype data and the new data actually. So we are applying the loss functions between them, which are like cluster loss. We are trying to keep the prototypes distinct in the same class. So if two prototypes are in the normal class, then we want to keep them distinct. So we apply a loss function of that, and also the separation of them. That's because if the prototypes are in a different class, so if one of them shows the attack pattern, one of them is showing the normal pattern, then they should be they should show so much distinction actually. So they shouldn't be placed in the near way, so they should fall apart. So we are applying these losses to create 16 different placed prototypes, and then do the prediction based on this. And then when you see any like the data which is really close to one prototype, that's in which we are showing an attack pattern, then we name the data shows the attack pattern because it's close to the prototype node. And the second algorithm in our logic is the contrastive edge graph neural network, which has a dual head architecture. And if we take a closer look, then the path actually to the classification head is completely same with the EdgeLevelGCN. But here we have changed our loss function a little bit. We are applying right now the contrastive loss, which is basically calculated with the projection head. So the projection head is more or less the same, the EdgeLevelGCN layered architecture, but as you see, we are applying to architecture, like 2-layered neural network instead of 3. So that means we have the 128 dimensional data afterwards, and we apply L2 normalization between them, and also some parameters as well, like temperature and so on, to normalize these weights. And then we found a contrastive loss of them. And then we apply this contrastive loss with the loss coming from classification, which is like the EdgeLevelGCN. The 128 is our selection. Actually, it can be hyperparameter. It is interchangeable for sure, as well as this temperature that we are applying for the contrastive loss. And that's basically the formula of the contrastive loss. So here, actually, what this architecture presents is kind of a different loss function, which will basically have a different and, so to say, better results. The third architecture that we are basically proposing, and so also some examples, is the GSL-GNN, which also shows two parts. And as you see right now, the right path named like original topology, in which we are basically calculating the original topology. This right part is from the EdgeLevelGCN as well, so it's completely the same. But then on the left part, we have some magic and novelty, in which we are creating a new graph with the structural learner. So we apply a parameter which is 15 actually. We have created a new graph by taking the differences of the data of the raw packages, and these differences, we create a matrix with this 15 distinction. The rest, actually, we have more distinction as well, but we keep the first 15, which shows a better value, and then we created our new graph based on this. So that's kind of the idea behind the structural learner part. And then we apply the layer based on to reduce its dimension, actually. And then we are having some values from structural learner. We have some values from the original topology as well. We are applying the graph fusion to combine them. So we take the half model of this left part, and the half model of this from the original right part. And then we have the core model afterwards. Then we apply the edge classification afterwards. So we have two separate layers afterwards, attack and normal. Then we start predicting the output, actually. Why we are creating this graph again is we are trying to find the hidden relationship between the nodes, actually. That's the core idea behind, because we are applying the subtraction between the data of the node directly, and we might see that if two nodes which are really like far away, we can also like have subtract their relations. So when we subtract these two separate nodes, if we had a data which is like kind of more than the others, then we basically discover the relationship between the nodes which are really far away, the IP addresses. So that's the core idea. Actually, we discovered the hidden relationship. We also discovered the original topology, and then we combine them. So to summarize this algorithm. And then we can start our experiment. After explaining the methodology, we have actually used the TON IoT dataset. That means which will include some the raw packages coming from the real devices. So that's why we have actually selected this the dataset. And we actually saw that it's when we take the data set, we saw it's 99% showing the attack ones, while the 1% shows the normal. So we need to create like another data set to balance them actually. So we to give the numbers with the same values actually, like the normal ones and the attack ones. So we have created a combined dataset from this dataset actually, get the entries to balance it. And we then apply the data processing actually. We have created graph snapshots, which are parts of graphs, smaller graphs, that since the graph is could be huge, we have actually started using graph snapshots, which will each snapshot has around 3,000 connections. And then with the balance, from the balance data set, we have created these snapshots, and then we have actually split them. So 70% for the training is 140 snapshots, and 30 snapshots for the validation and test as well. And then we start applying our algorithms and get the results actually. So here we see the EdgeLevelGCN in this combined balanced data set. It has around 91% accuracy, while the Prototype-GNN has 95, and the Contrastive-GNN is also close to 95, better accuracy than the Prototype-GNN. But here, actually, this metric, which will basically penalizes the missed attack ones, shows a better percentage from the Prototype-GNN if we compare the Contrastive-GNN and Prototype-GNN. And we actually saw that the highest accuracy is from the GSL-GNN, and which gives us some ideas. So the improvements from the baseline is in case of the accuracy, as in GSL-GNN, it's much more high than the Contrastive-GNN and Prototype-GNN. So that means if we discover the hidden relationship between the IP addresses in the graph, then we will have a high accuracy as well. But if we take a closer look on the architectures that we are proposing, actually, we have a higher accuracy in the GSL-GNN, but we actually saw that it's a little bit costly because the time that we have spent on the training of the algorithm is more or less 10 times higher than the other ones. And we actually saw that with another metric, ROC-AUC. Let me show this here. We saw that it's high in the Contrastive-GNN. And that means if we want to penalize the missed attacks, if we have an architecture that in which we don't want to miss any attack ones, or maybe miss very, very small of them, that means we can use Contrastive-GNN. And the Prototype-GNN it can be interpretable. That's because we can basically change the numbers of the prototypes. So in our architecture, we are using 16, but one can use like 24, 30, and so on. That means we can interpret the data that comes to our side. Maybe if we have a multi-class, instead of labeling normal and attack, maybe we can use more prototypes. If we have 5 or 10 classes, let's say, if we give 5 prototypes for each, then we will have a much more different architecture by just changing some hyperparameters. That means it's easily configurable as well and interpretable. The EdgeLevelGCN shows a rapid baseline to us. So if we want to use the algorithms in faster times, then maybe we can select our baseline algorithm for sure. And that means also, while I was mentioning the results of the algorithms, I also had some future works currently, as I showed in the architectures, we are using some loss functions like contrastive loss and some normalizations as well. If we want, maybe we can, if we change these normalizations and loss functions, we might have a different results at the end. so which will basically yield us a different academic work. So that's kind of one feature aspect. Another one is currently we are labeling them attack or normal, but we can do multi-class classification as well. So we can like the attack, especially the attack labeled ones, we can separate them into different classes like backdoor, man in the middle, and so on. And since we balanced our data set in the third aspect, like since we balanced our data set, maybe we can use an extreme imbalanced data set with really high hidden dimensions in these neural network layers of our algorithms. So currently, as you saw, we have used 128, as I mentioned. But if we use like 1,000 hidden dimensions with this extreme imbalanced data set, that will basically show us a different work as well. And maybe with respect to this different environments that we want to use the algorithms, we can fine tune them or like apply these algorithms in different environments as well. This can be one more feature work as well. With that being said, actually, I am currently at the end of my presentation. Thank you for your listening. If you have any questions, I can reply. If you have questions that are coming up after my presentation, you can reach me via this contact information and so on. So thank you for your listening.
Thank you, Dr. Mehmet. It's a great presentation. Does anyone have any question? Are there any questions from forum? I have some questions for you, Dr. Mehmet, if you don't mind.
Yeah.
Is it possible to extend the Prototype-GNN architecture to handle unsupervised intrusion detection?
I think it's possible, since basically since it also yields the relation in which the nodes are a little bit far away. So if it basically discovers the hidden relationship between them, I think it's possible, because it's we are also applying the graph neural network at the same time, which will have meaningful like extractions from the neighbors of the nodes. So I think it should be doable.
Yeah, that's great. Thank you, Dr. Mehmet. And if you don't mind, there is one more question. In the real-time network traffic, in which the pattern of attacks will evolve over time, how does the GSL-GNN model will work or handle this situation? You mentioned in your earlier slides.
Should I come back to the slide or?
No, it's okay. It's okay.
Okay. So it's since like it's kind of a deep learning algorithm, it will also show us the like main machine learning step, which means, for example, we have network data coming up, independent of its huge or not. We can train this algorithm with the data set. And then we create our models, actually. So after the training, the GSL-GNN model is created. When the new data comes to our devices, let's say we are using some devices in our environment and the new data is coming up with respect to the model that we have just trained with the GSL-GNN, we can start predicting the new coming IoT data based on this model. So labeling them normal or attacks. If we are applying multi-class, we can maybe separate its classes as well. We can detect that's showing a man-in-the-middle attack. We can detect that it's showing a DDoS attack, and so on. So basically, it's I can apply this in the basic machine learning step. We train with the big data. We created our models for the GSL-GNN. And when the new data comes, we can start using this GSL-GNN to predict the new data.